Somewhere out in the dark, two dead stars are falling toward each other. Not stars in the way you imagine them, glowing balls of fire, but the crushed leftover cores of stars that already died. Each one is barely wider than a city, yet packs more mass than the sun. And when they finally slam together, something impossible happens. In the debris of that collision, brand new atoms are forged. Atoms that could never have been built inside an ordinary star. Gold, platinum, uranium, elements that make up wedding rings, catalytic converters, nuclear reactors. Not made in furnaces, made in the fireball of a corpse, smashing into a corpse. Tonight, we're going to unpack what really happens in that instant. How much of the gold on Earth was born inside a dying scream. Before we dive in, if you enjoy these deep explorations of what's really happening out there in the universe, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. To understand what happens when two dead stars collide, we first have to understand what a dead star actually is. Because when someone says a star has died, most people picture a candle burning out, a quiet fading. That is not what happens. Not for the kinds of stars we are talking about tonight. Every star, including our own sun, is a balancing act. Deep in its core, hydrogen atoms are being crushed together to make helium, and that fusion releases an enormous amount of energy pushing outward. At the same time, the entire weight of the star, hundreds of thousands or millions of times the mass of Earth, is trying to collapse inward under its own gravity. As long as the fusion keeps going, those two forces stay in balance. The star shines. It stays stable for millions or billions of years. But every star eventually runs out of fuel. And when it does, the outward push disappears, and gravity finally wins. For a small star like our Sun, that ending is relatively gentle. The core collapses into a hot, dense object about the size of Earth, but with roughly half the mass of the Sun packed into that Earth-sized ball. That leftover core is called a white dwarf. It is dense. A teaspoon of white dwarf material would weigh several tons on Earth. But it is not the extreme case we need to talk about. If the dying star is more massive, if it started out with maybe 8 or 10 times the mass of our Sun, something much more violent happens. The core collapses so hard, so fast, that the collapse itself triggers an explosion. That is a supernova. In a matter of seconds, the star tears itself apart, releasing more energy than the Sun will release in its entire 10 billion year lifetime. Most of the star gets flung outward into space at speeds of thousands of kilometers per second. But at the very center, where the core used to be, something is left behind. That something is a neutron star. To call it a star is almost misleading. Nothing is fusing, nothing is burning. It is not really a star in any normal sense. It is a corpse, a crushed remnant. But even calling it a corpse does not quite capture what has happened, because the matter inside it has been squeezed into a state that does not exist anywhere else in the universe under normal conditions. Here is the scale. A typical neutron star is only about 20 kilometers across. 20. That is smaller than most major cities. You could fit the entire object inside the ring road of a mid-sized town. And yet, inside that 20-kilometer sphere, there is more mass than the Sun contains in its entire body. Somewhere between 1.4 and 2.3 times the mass of the Sun, all crushed into a ball the size of a city. The density is almost impossible to describe accurately. A single teaspoon of neutron star material would weigh roughly 1 billion tons on Earth. Not a million. A billion. If you could somehow scoop out a sugar cube-sized piece of a neutron star and set it down in the middle of a city, it would punch straight through the ground, through the crust, and keep going. Pulled downward by its own extreme gravity. That kind of density does something strange to matter itself. Under normal conditions, atoms are mostly empty space, a tiny nucleus in the middle, then a huge cloud of electrons around it. But in a neutron star, the pressure is so extreme that the electrons get crushed into the nuclei. Protons and electrons merge, becoming neutrons. Almost the entire star ends up being a soup of neutrons, packed so tightly that they are basically touching. That is where the name comes from. It is not just a metaphor. The star really is made of neutrons. The surface of a neutron star is theorized to be a thin crust of extremely dense ordinary matter, perhaps only a kilometer thick. Below that, the neutron soup begins. And deeper still, in the very core, the pressure gets so extreme that even neutrons might break apart into something even more exotic. States of matter physicists are still arguing about today. We cannot go there. We cannot recreate those conditions in any laboratory on Earth. Every attempt to describe what is happening inside the deepest layer of a neutron star is an educated guess, refined by watching how the star responds to being poked and prodded from the outside. Gravity on the surface of a neutron star is roughly 200 billion times what you feel on Earth. If you could somehow drop a marshmallow from a height of 1 meter above a neutron star, it would hit the surface at a speed of thousands of kilometers per second, and the impact would release energy comparable to a small, conventional bomb. Not because the marshmallow is dangerous, because the gravity is that intense. Some neutron stars also carry magnetic fields trillions or even hundreds of trillions of times stronger than Earth's, so intense they would rip apart any ordinary matter that got close enough, and many of them are spinning. Some spin so fast that they complete a full rotation hundreds of times every second. That means an object more massive than the Sun, 20 kilometers wide, is turning over itself hundreds of times in the span of a single heartbeat. This is what a dead star looks like when it is at its most extreme. When one of these fast-spinning neutron stars sweeps a beam of radiation past Earth, we detect it as a pulsar, a lighthouse-like blip repeating with clockwork precision. Astronomers have used pulsars to build some of the most accurate clocks in the universe. And it was through pulsars, decades ago, that we first found direct evidence of gravitational waves. Not because we detected the waves themselves at first, but because we watched a binary system of neutron stars lose energy over years of patient observation, exactly as Einstein's theory predicted, gradually spiraling closer with each passing orbit. That binary, discovered in the 1970s, was our first hard proof that neutron stars really do dance toward each other in the way we're about to describe. The astronomers who found it were later awarded the Nobel Prize for the discovery. Long before we could hear a merger directly, we could watch one preparing itself, invisibly, in slow motion. One neutron star sitting alone in space is already almost impossibly strange. But the universe, being what it is, likes to make things in pairs. Massive stars are often born in pairs. Two stars condense from the same cloud of gas at roughly the same time, and they end up orbiting each other. Astronomers call these binary systems. And because massive stars tend to die relatively quickly, if you start with two very massive stars in a binary, both of them are going to end their lives in supernova explosions within a few tens of millions of years of each other. Sometimes those explosions unbind the system entirely. One of the supernovae kicks its remnant out of the pair, and the two objects go their separate ways into the galaxy. But in a certain fraction of cases, the pair survives. Both stars explode. Both leave behind neutron stars, and those two neutron stars remain in orbit around each other, still bound by gravity. That is the setup. That is the system we care about. Two crushed, city-sized remnants of stars that already died in supernova explosions, orbiting each other in the darkness. No light, no fusion, just gravity holding them together in a slow, silent dance. Systems like this exist, but they are rare. Astronomers estimate that in a galaxy like our own Milky Way, a merger of two neutron stars might happen only once every 30,000 to 100,000 years. So while the sky is full of neutron stars, most of them are alone, and most binary systems will never live long enough to reach the point of collision. The ones that do are special. They are the survivors of a very specific sequence of stellar deaths, and they carry the seeds of an event that only happens somewhere in a galaxy like ours now and then, on timescales far longer than any human civilization. You might assume, given how tiny neutron stars are and how much empty space is out there, that a pair of them would just orbit each other forever. Two dark specks, endlessly circling. Nothing to disturb them, but that is not what happens. Because when two very massive objects orbit each other, they do something remarkable. They shake space-time itself. To understand this, you have to hold on to an idea Einstein gave us a little over a century ago. Space and time are not a passive background against which things move. Space and time are a single, flexible thing, a fabric that can be bent and stretched by mass. Anything with mass distorts this fabric. Earth does. The sun does. You do, technically, although your mass is so small that the distortion you cause is far too tiny to detect. But if you take two neutron stars, each with more mass than the sun, and spin them around each other quickly, they do something you can actually measure. They generate ripples, waves in the fabric of space-time that travel outward at the speed of light. Every time the two neutron stars sweep around each other, they send out a pulse of these waves, gravitational waves. And here is the critical detail. Those waves carry energy that has to come from somewhere. And where it comes from is the orbit itself. Every gravitational wave the pair sends into the universe is energy leaving the orbit. The two neutron stars are, in a very real sense, radiating away the energy that keeps them at a comfortable distance. So over time, that orbit shrinks. The two objects drift closer together. Not because anything is pushing them, not because they are running into anything, purely because their own motion is bleeding energy into gravitational waves, and there's nothing they can do to stop it. At first, the process is agonizingly slow. When two neutron stars are separated by, say, a distance comparable to the gap between Earth and the Sun, the amount of energy leaking into gravitational waves per year is minuscule. Their orbit shrinks by only a fraction of a millimeter over an entire year. If you started with a wide, healthy neutron star binary and watched it for a normal human lifetime, you would not notice anything at all. The two stars would seem to just orbit each other, unchanged. But over hundreds of millions of years, or billions of years, that infinitesimal energy loss adds up. The orbit gets smaller. And here is the terrifying part. As the orbit shrinks, the two neutron stars orbit each other faster. And the faster they orbit, the more powerful the gravitational waves they emit. And the more powerful the waves, the more energy they lose. And the more energy they lose, the smaller the orbit gets. It is a runaway process. At the beginning, the shrinking is so slow it is basically invisible. But as the two objects get closer, everything accelerates. What took 100 million years at the start might take 100,000 years toward the middle. Then 1,000 years, then a year, then a day, then an hour. Astronomers call this the inspiral. It is a beautiful, chilling word for what is really happening. Two dead stars, spiraling inward toward each other, faster and faster, unable to stop. By the time the two stars are separated by only a few thousand kilometers, they are orbiting each other several times per second. By the time the separation is down to a few hundred kilometers, they are whipping around each other more than 100 times a second. The frequency of the gravitational waves themselves is climbing rapidly, sweeping upward through the range of human hearing. If you converted the final second of a neutron star inspiral into sound, you would hear a chirp, a rising tone that starts low and screams upward until it cuts off in an instant. That is not a metaphor. Astronomers who study these signals literally listen to them as chirps. In the final seconds before the collision, the situation becomes almost absurd. The two neutron stars are separated by only a few hundred kilometers. Each object is roughly 1.5 times the mass of the Sun, traveling at a significant fraction of the speed of light along its orbit. The gravitational waves they are emitting in that last second are so powerful that if the merger happens close enough to Earth, our detectors can pick them up from tens of millions or hundreds of millions of light years away. For a brief instant, this pair of dead objects is one of the loudest sources of gravitational waves in the observable universe. Then, in the last fraction of a second, they touch. I want to slow down here because there is a distinction that is easy to blur. The collision itself, the moment when the two neutron stars actually come into contact, is not what a kilonova is. The collision is over almost instantly. In less than 1,000th of a second, the two objects have crashed into each other and become one. The gravitational wave signal peaks in that instant, then abruptly ends. That is the merger. That is a specific sub-second event. The kilonova, the thing we came here to talk about, is what happens next. It is a slower story. It plays out over hours and days, and it is powered by material that has been ejected during the collision. That material carries the seeds of what will become the heaviest elements in the universe. But the physical event we can see as light, as an actual glow that spreads across the sky, is not the collision. It is the aftermath. That distinction matters because a lot of different things happen during a neutron star merger, and they are often confused with each other in casual conversation. Let me untangle them. First, there is the merger itself. That is the physical collision of the two neutron stars. It is over in less than a millisecond, and the direct signature we detect from it is gravitational waves, not light. The gravitational wave signal is the ripple in space-time that we can measure on Earth using extraordinarily sensitive instruments. It tells us that two very compact objects, each roughly the mass of a star, just spiral together at nearly the speed of light. But the waves themselves are not light. They are distortions in space-time, and they pass through Earth without heating anything or lighting anything up. They travel through us. Second, there is a possible short gamma ray burst. When the two neutron stars slam together and form a rapidly spinning, ultra-dense remnant, that remnant may launch a jet of matter and radiation moving at nearly the speed of light. If that jet is aimed roughly at Earth, we see a brief, intense flash of gamma rays, the highest energy form of light. These flashes typically last less than 2 seconds. That is a short gamma ray burst, but it is not the kilonova. It is a separate emission from a different part of the same event, and it is only visible to us if the jet happens to be pointing in our direction. Third, there is the kilonova itself. This is not the collision, and it is not the gamma ray flash. This is a much broader glow, spread across visible and infrared wavelengths, powered by radioactive material that has been thrown out of the collision zone. The kilonova brightens and fades over the course of days. And crucially, you do not need the jet to be pointing at you to see it. The material glows in every direction. So even if the gamma ray beam misses Earth entirely, the kilonova itself can still be visible, provided the merger is close enough for us to detect the light. I want to stack this against a few related events people sometimes confuse with a kilonova. A classical nova is a completely different phenomenon. It happens when a white dwarf, one of those Earth-sized stellar remnants, siphons hydrogen off a companion star and eventually detonates it in a runaway fusion reaction on its surface. A classical nova brightens for weeks and involves ordinary fusion. It is orders of magnitude less energetic than a kilonova, and it has nothing to do with neutron stars. A supernova is the explosion of a massive star at the end of its life. It happens once per star when the core collapses. Supernovae are far brighter than the kilonovae in total light. They can shine for weeks or months, and they involve blasting the outer layers of a single star into space at high speed. A neutron star may be left behind afterward, but the supernova itself is a stellar death, not a merger. A hypernova is essentially an extreme supernova, thought to occur when a very massive, fast-spinning star collapses in an especially violent way. Hypernova are sometimes associated with long gamma ray bursts, which typically last longer than a couple of seconds and come from very different physics than the short gamma ray bursts linked to neutron star mergers. So the family looks like this: classical nova, a white dwarf hiccup; supernova, one massive star dying; hypernova, one even bigger star dying in a nastier way; kilonova, two dead stellar cores colliding. The kilonova is the odd one out. It is not one star dying, it is two corpses meeting. And the name kilonova can be misleading. It was chosen because early estimates suggested this kind of event should be roughly 1,000 times brighter than an ordinary nova at peak. Kilo meaning 1,000. But the label is a rough shorthand. A kilonova is not literally 1,000 times more energetic than every nova in every measurable sense. It is a whole different physical process, powered by something ordinary novae have no access to. There is also a second kind of system that can produce a kilonova, and it is important not to skip over. Everything I have described so far involves two neutron stars, but you can also, in principle, get a kilonova from a neutron star merging with a black hole. Picture the setup. A neutron star and a stellar mass black hole, both born from separate supernovae in the same binary system, are locked in an ever-shrinking orbit. Same story as before. Gravitational waves bleed away orbital energy. The inspiral happens. But when the neutron star finally reaches the black hole, the outcome depends on the details. If the black hole is much more massive than the neutron star, or if the black hole is not spinning fast enough, or if the orbit brings them together in the wrong geometry, then the black hole simply swallows the neutron star whole. The neutron star crosses the event horizon and disappears. Nothing gets thrown outward, no debris, no glow. In that case, there is a gravitational wave signal, but no kilonova. The event is essentially invisible to any telescope pointed at the sky. The scenario that does produce a kilonova is more delicate. The black hole has to be small enough, or spinning fast enough, or the orbit has to bring the neutron star close enough that the neutron star gets torn apart by tidal forces before it crosses the event horizon. In that case, some of the neutron star material is flung outward instead of being swallowed. That flung material is the same neutron-rich stuff that fuels a kilonova in the 2 neutron star case. And so the aftermath can look similar. So it is not accurate to say that every neutron star merging with a black hole produces a kilonova. Some do not. It depends on the mass ratio, the spin of the black hole, and the exact geometry of the encounter. For the rest of this story, we are mostly going to focus on the 2 neutron star case, because it is cleaner, and because it is the case we have observed directly. But keep in the back of your mind that the neutron star and black hole channel exists too, and that it likely contributes to the overall population of kilonovae in the universe. Now, come back with me to those final seconds before the collision. 2 neutron stars, each more massive than the Sun, each only about 20 kilometers across, are separated by only a few hundred kilometers. They are whipping around each other so fast that they are practically blurring into a single blob. The gravitational waves streaming outward from the pair are the loudest gravitational wave signal in the observable universe at that moment, briefly outshining, in gravitational wave energy alone, every ordinary star in a large galaxy combined. And then they meet. At the instant, 2 objects that used to be independent become a single, wildly hot, wildly distorted mass of neutron-rich matter. The relative velocity at contact is a large fraction of the speed of light. The surface temperatures spike to hundreds of billions of degrees. Enormous portions of the material get compressed even further, briefly reaching densities beyond what existed inside either original neutron star. Almost none of that is what you would call an explosion in the everyday sense. There is no shockwave through open air. There is no flame. There is just an unimaginably violent collision of ultra-dense matter with itself, in a place where the ordinary laws of physics are being pushed to their limits. And yet, from that collision, something very specific begins to happen. Material starts to be flung outward. Some of it is torn off by tidal forces just before the 2 stars touch. Some of it is squeezed out at the moment of contact, like toothpaste from a tube being crushed under a tank. Some of it will be blown off later from the disk of debris that forms around whatever the merger leaves behind. All of that ejected material has a very particular property that ordinary stellar material does not have. It is drenched in neutrons. Free neutrons everywhere at densities you cannot get in any normal environment in the universe. And it is that neutron-rich debris expanding outward into space at a significant fraction of the speed of light that is going to build gold. Not now. Not in the first instant. But in the seconds and minutes and hours that follow the collision, as the neutron soup expands and cools, atomic nuclei inside it are going to swallow those free neutrons in enormous numbers and climb, atom by atom, up the periodic table into elements that no ordinary star could ever make on its own. That is where the kilonova truly begins. Not in the moment of contact, but in the moment right after, when the debris starts to expand and the physics of building heavy elements takes over. But before we can watch that debris start to glow, we have to understand exactly how it escapes. Because the story of how matter gets thrown clear of 2 colliding neutron stars is stranger and more delicate than you might expect. To understand why gold ends up scattered through space after a neutron star merger, you have to understand something that sounds almost paradoxical. Most of the material inside the two neutron stars never leaves. It stays trapped. It gets absorbed into whatever the merger creates. Only a small fraction, a tiny slice of the total mass, actually gets flung far enough and fast enough to escape the gravitational grip of the collision. But that tiny slice is where everything happens. Think about the situation. You have two objects, each roughly 1.5 times the mass of the Sun, crushed into spheres only 20 kilometers across. The surface gravity is 200 billion times what you feel standing on Earth. If you dropped an object toward the surface of one of these stars from just a meter above it, the object would hit the surface moving at a significant fraction of the speed of light. Nothing escapes a neutron star easily. The gravity is too strong. So when two of these objects collide, you might expect that everything just gets sucked into the merged object. That the collision is more like a merger of two beads of mercury than an explosion. And in a certain sense, most of the mass does exactly that. It falls together, forms a hot, dense, wildly spinning remnant, and stays put. But not all of it. A small fraction, somewhere between a few hundredths and maybe a tenth of the mass of the Sun, gets thrown outward with enough velocity to actually escape. That does not sound like much. A few percent of a stellar mass. But if you convert that into more familiar units, it is somewhere between 10,000 and 100,000 times the mass of Earth, flung into space in a matter of seconds to minutes. And it is not ordinary matter. It is matter drenched in free neutrons, matter that carries the seeds of gold and platinum and rare earth elements. That is the ejector. That is the material that will build the Kilonova. Astronomers think this ejector escapes through 3 main channels, and it is worth understanding each one separately, because they behave differently. They carry different amounts of material, and they leave different fingerprints on the light we eventually see. The first channel is called tidal ejector. Tidal forces are the same physics that produces ocean tides on Earth. When one object is close to another, the side of it facing the other object is pulled harder than the far side. That difference in pull stretches the object. For Earth and the Moon, the effect is subtle. The ocean bulges by a meter or two. But when you scale this up to 2 neutron stars whipping around each other at nearly the speed of light, tidal forces are not subtle at all. They are catastrophic. In the last moments before the 2 neutron stars actually touch, they are close enough that each one is tearing at the other. The gravity of each star is pulling on the near side of the other star much harder than on the far side. And because neutron stars are not perfectly rigid, they respond, they stretch, they deform. Long tongues of neutron star material get pulled out into the space around the pair, curving and spinning with the motion of the orbit. Some of that stretch material gets flung outward hard enough to escape entirely. It sprays out along the equatorial plane of the orbit, in the same flat sheet where the 2 stars were dancing. Because it is coming from deep inside the neutron stars, it is extremely dense, extremely neutron-rich, and moving fast, but not at the speed of light. Typically, tidal ejector moves at somewhere between 10 and 30% of the speed of light. That is fast enough to escape the system. It is slow enough that we would say it is not relativistic in the way a laser beam is. The exact amount of tidal ejector depends heavily on how the merger unfolds. If the two neutron stars have very different masses, so that one is significantly bigger than the other, the smaller one gets shredded much more brutally than a similar sized companion would. In that case, more tidal ejecta gets flung outward. If the two stars are nearly identical in mass, they mostly just fall into each other, and less tidal material escapes. So already, you can see that no two mergers are going to produce exactly the same debris. The second channel is shock-heated ejecta. This is what happens at the exact moment of contact. When the two neutron stars actually crash together, the interface between them, the region where their surfaces meet, becomes a place of unimaginable violence. Two ultra-dense objects, moving at a large fraction of the speed of light, are ramming into each other. The material at the collision boundary gets shock-heated to hundreds of billions of degrees Kelvin. Some of it gets squeezed sideways so hard that it squirts out perpendicular to the direction of motion, like water bursting sideways when two hands slap together underwater. Shock-heated ejecta is different from tidal ejecta in a few important ways. It is hotter, it is more spread out around the collision, rather than being confined to a thin sheet in the orbital plane. And critically, its neutron richness can be different. Because the material has been so violently heated, weak nuclear reactions can convert some of the neutrons back into protons before the ejecta expands and cools. That changes its composition. It ends up somewhat less neutron-rich than the tidal ejecta. That distinction is going to matter enormously when we talk about which elements get built. Because the more neutrons you have available compared to protons, the heavier the elements you can construct. Tidal ejecta, drenched in neutrons, tends to build the very heaviest elements. Shock-heated ejecta, with somewhat fewer free neutrons per proton, tends to build lighter elements in the heavy category. Same collision, different debris streams, different chemistry. The third channel is disk wind ejecta, and this one takes longer to develop. After the collision, whatever is left at the center is not just a single compact object sitting quietly in the wreckage. It is surrounded by an accretion disk. Some of the material from the two neutron stars that did not immediately fall into the remnant and did not immediately escape ends up in a swirling disk around the central object. It orbits. It gets hot. It is dense. Densities in this disk can approach the densities inside the neutron stars themselves, though somewhat lower. Over the next tens of milliseconds to seconds and even minutes, that disk does what accretion disks always do. It slowly funnels material inward toward whatever is at the center, while at the same time throwing material outward through winds. Winds in this context mean streams of matter driven off the surface of the disk by a combination of magnetic fields, radiation pressure, and viscous heating. It is the same basic process that drives the solar wind streaming off our own sun, except vastly more intense. Disk winds are the slowest and typically the least energetic of the three ejecta types, but they can carry a lot of mass. In many mergers, the disk winds account for more of the total ejected material than the tidal or shock-heated components combined, and their composition depends heavily on what is happening at the center of the system, which is the next thing we need to talk about. Because here is the crucial fact that shapes everything about how much material escapes and what it is made of. The nature of the object at the center of the merger, the thing left behind after the collision, changes everything. And there are 4 possible outcomes. The first possible outcome is what astronomers call a hypermassive neutron star. This happens when the combined mass of the two neutron stars is above what a neutron star should be able to support against gravitational collapse under normal circumstances. But the merged remnant is spinning so fast, and internal pressure gradients are so extreme that it briefly holds itself up anyway. A hypermassive neutron star is a temporary thing. It lives for milliseconds, maybe up to a second. Then, as it sheds angular momentum through gravitational waves and internal magnetic braking, it can no longer support its own weight, and it collapses into a black hole. The second possible outcome is a supramassive neutron star. This happens if the combined mass is a bit lower, so that centrifugal support from fast rotation alone is enough to hold the object together, even without the extreme internal pressure gradients of a hypermassive state. A supramassive neutron star can live longer, seconds, minutes, maybe even hours or days, depending on how quickly it spins down. Eventually it too collapses into a black hole, but it holds on much longer than a hypermassive one. The third possible outcome is a long-lived neutron star, or in principle, even a stable one. If the combined mass of the two neutron stars is low enough, the remnant might be a normal neutron star that never collapses at all. It just sits there, a hot, rapidly spinning object, spinning down over cosmic timescales. Whether this actually happens depends on some fundamental physics that we still do not fully understand. The maximum mass that a neutron star can support before collapsing is set by the details of how neutron-rich matter behaves at extreme densities, and that is one of the biggest open questions in nuclear physics right now. The fourth possible outcome, and in many cases the most likely one for two neutron stars whose combined mass is on the higher end, is prompt collapse to a black hole. In this case, the two stars merge, and within about a millisecond the whole thing collapses into a black hole. There is barely any time for a stable rotating remnant to form. The event horizon swallows most of the material almost immediately. Now, why does all of this matter for the kilonova? Because the type of remnant determines how much ejecta escapes, and just as importantly, what that ejecta is like. If the remnant is a hypermassive or supramassive neutron star that lives for at least tens of milliseconds, something crucial happens. The remnant is extremely hot. Its interior temperature is measured in tens of billions of degrees Kelvin, and at those temperatures, it emits enormous numbers of neutrinos. Neutrinos are ghostly, nearly massless particles that barely interact with ordinary matter. In everyday life, you can basically ignore them. Trillions of neutrinos from the sun are streaming through your body right now, and you will never notice any of them. But in the immediate vicinity of a hypermassive neutron star, the density of neutrinos is so extreme, and the density of matter is also so extreme, that the neutrinos actually do interact with the ejecta in significant numbers. Specifically, neutrinos can convert neutrons into protons through what are called weak nuclear reactions. A neutron catches a neutrino, or more accurately, an anti-neutrino of a certain kind, and turns into a proton, releasing an electron in the process. Or the reverse can happen, with a neutrino converting a proton back into a neutron. Which reaction dominates depends on the specific type of neutrinos being emitted and the conditions of the ejecta. The important point is that a longer-lived neutron star remnant exposes the surrounding ejecta to a longer, more intense bath of neutrinos. And that bath tends to raise the proton fraction of the ejecta. It makes the material somewhat less neutron-rich than it would otherwise be. This has huge consequences for which elements will eventually be built. If the ejector has plenty of free neutrons compared to protons, the rapid neutron capture process, which we will unpack in detail shortly, can climb all the way up the periodic table into the heaviest elements. Uranium, gold at the higher masses, platinum, rare earths. But if the neutrino bath has shifted things toward more protons, the process cannot climb as high. It gets stuck at lighter elements in the heavy category: strontium, yttrium, elements that are still much heavier than iron, but not the truly heavy stuff. So the paradox is this: if the merger prompt collapses into a black hole, the ejector gets less neutrino irradiation, because a black hole does not emit neutrinos from its surface the way a hot neutron star does. That means the ejector stays more neutron-rich, and it can build heavier elements. But there is less time for the disk to develop, and less ejector overall. If instead the merger produces a long-lived neutron star, there is more ejector, but that ejector gets bathed in neutrinos for longer, becomes less neutron-rich, and builds a somewhat different mix of elements. There is no single answer to the question of what a merger produces. Every merger has its own unique combination of masses, spins, and remnant lifetime. And because of that, every kilonova is expected to look a bit different from every other one. There is no template. There is no universal kilonova. There is a family of events, related but not identical, each one carrying the fingerprints of the specific collision that made it. Now, let me try to put this in a visual picture, because the geometry of the ejection matters a lot for what we eventually see. Picture the merger as happening in a flat plane, the orbital plane of the two neutron stars. Along that plane, the tidal ejector gets flung outward first, in a thick disk of highly neutron-rich, relatively slow-moving material. Some of it is moving out into space at 10% of the speed of light, some at 30%. It fans out along the equator of the system. Then, at the moment of collision, shock-heated ejector squirts out in a slightly different direction. Some of it goes forward along the equator, mixing with the tidal material, but some of it goes upward and downward, out along the axis perpendicular to the orbital plane. And that upward and downward material is significant, because it is being launched into the polar regions, where the ejector cloud is otherwise relatively thin. Then, over the next milliseconds and seconds and minutes, disk winds start blowing off the accretion disk that has formed around the central remnant. These winds go primarily outward from the disk, so mostly along a broad range of angles somewhat above and below the equatorial plane. The composition of these winds depends on the disk conditions and on how much neutrino irradiation the disk is receiving from the central object. The end result is a fundamentally lopsided cloud of debris. Along the equator, you get a very neutron-rich, relatively dense component. Above and below the poles, you get a somewhat less neutron-rich component, driven up there by shock heating and by some of the disk winds. And the boundary between these zones is not sharp. Different types of ejector blend into each other in complicated ways. This asymmetry is going to matter enormously when we think about what the kilonova looks like from different angles. If you happen to be viewing a merger from directly above the pole, you are looking down the axis of the system, and you see mostly the polar component of the ejector. That component tends to be somewhat less neutron-rich, which means it will build lighter, heavy elements. It will glow brightly at shorter wavelengths for a while, in the blue and ultraviolet, before fading. If instead you are viewing the merger from the side, edge on, you are looking through the thick, neutron-rich equatorial disk. That disk is going to be full of the heaviest elements, and those elements have a particular property that we will explore in detail in a moment. They absorb short wavelength light incredibly efficiently and re-radiate it at longer wavelengths. So an edge-on view of a kilonova is going to be dominated by red and infrared light, not blue. Two observers watching the same merger from different angles are going to see slightly different things. Same event, different light. This has been one of the trickier aspects of interpreting the handful of kilonovae we have actually observed. You cannot just assume that what you see is the whole picture. You have to reason about geometry. Let me pull back for a moment and talk about the raw numbers, because they help put the scale of what is happening into perspective. The total mass ejected from a typical neutron star merger is thought to be somewhere in the range of 1/100th to 1/10th the mass of the Sun. That is a very approximate range. Some mergers may eject less, some more, depending on the specifics. The exact amount is one of the things kilonova observations are helping us pin down. That is not much compared to the total mass of the two neutron stars, which combined would be around 3 times the mass of the Sun. The vast majority of the material stays in the remnant, but even 1/100th of the solar mass, converted into gold and platinum and heavy elements, represents an absolutely staggering amount of material by any earthly standard. Rough estimates from one well-observed event suggest a single merger can synthesize somewhere on the order of an Earth's mass of gold, though the number depends heavily on the specific merger and the details of the ejector. Some events produce more, some produce less. Nobody counted the atoms one by one. The estimate comes from modeling how bright the glow was, how it changed color, and what elements had to be present in what quantities to produce that particular light curve. Of that total ejected mass, only a certain fraction is going to end up as gold. Most of it will be other heavy elements, especially in the rare Earth family, and elements around strontium and yttrium. Gold is one product of the rapid neutron capture process, but it is not the only product, and it is not even the most abundant one. When you tally up everything a kilonova produces, gold ends up being a relatively small piece of the whole, though a very valuable one from a human perspective. The velocity of the ejector matters a lot for what we see. Most of the material is moving at roughly 10 to 30% of the speed of light. That is fast enough that the ejector cloud expands very quickly. Within seconds of the merger, the material has spread out to cover a region hundreds of thousands of kilometers across. Within minutes, millions. Within an hour, tens of millions. Within a day, the ejector cloud is bigger than the solar system. That expansion is important, because it means the ejector gets less and less dense over time, and that has a direct impact on when we can see any light from it. Immediately after the merger, the ejector is so dense and hot that any light produced inside it just gets absorbed by the surrounding material. The ejector is opaque to itself. You cannot see through it. All the radioactive energy being generated in the middle stays trapped. But as the material expands, it becomes more diffuse, and eventually light can escape. The point at which the ejector becomes transparent to its own light is a key moment. That is when the kilonova first becomes visible. And that moment is not the same for every wavelength or every part of the ejector. The polar regions, which are less dense, become transparent to visible light first. The equatorial regions, packed with dense material, stay opaque to short wavelengths for much longer. That is one reason a kilonova starts out bluer and then transitions to red. The bluer polar light escapes first. The redder equatorial light takes longer to break out. Okay, one more crucial piece of the picture before we move on, because I do not want to leave you hanging on it. Neutrinos again. I mentioned that neutrinos from a long-lived remnant can change the composition of the ejector. But neutrinos also matter for a completely different reason. They actually contribute to the energy budget of the merger. When a hypermassive neutron star forms, an enormous fraction of the total energy released by the collision goes into neutrino production. Something like 10 to 20% of the energy equivalent of the entire mass involved gets radiated as neutrinos in the first few seconds. This is more energy than the sun will release in its entire lifetime, dumped into neutrinos in a matter of seconds. Almost all of those neutrinos just fly out into the universe and are never seen again. Even if the merger happened relatively nearby by cosmic standards, the neutrinos would be almost impossible to detect because they interact so weakly with ordinary matter. But some of them interact with the ejector, and that interaction is what shifts the composition. Some of them also push material outward, adding to the disk winds. Neutrinos are a critical actor in this drama, even though they are invisible to almost all of our instruments. That is worth pausing on. When we watch a kilonova, we are seeing only a certain slice of the total energy the event releases. Gravitational waves carry away a huge amount of energy, which our detectors can pick up. Neutrinos carry away an even bigger fraction, and we mostly miss those. Kinetic energy of the ejector represents another substantial chunk. And what we actually see with our eyes and telescopes, the light of the kilonova itself, is only a small fraction of the total. Something like 1,000th or 10,000th of the total energy released by the event ends up as visible light. The rest is invisible to optical astronomy. So when you hear that a kilonova is one of the brightest transient events in the universe, that is true. But it is also worth remembering that we are only seeing a tiny sliver of what is really happening. The gravitational waves and neutrinos are carrying away most of the energy, silently, in ways that our eyes cannot see. Okay, I have been talking about ejector as if it is just neutron soup, but it is time to be more precise. The ejector is not literally made of neutrons alone. It is made of atomic nuclei suspended in an extremely dense, hot, neutron-rich environment. Those nuclei carry protons. They carry neutrons. They are actual atomic nuclei that used to be part of the crust or upper layers of the neutron stars. Iron nuclei, nickel, elements like that. And they are surrounded by a bath of free neutrons at densities you cannot get anywhere else in the universe. That is the setup for what happens next. Because now we have all these atomic nuclei sitting in a bath of free neutrons, and something remarkable is about to happen to them. Something that couldn't happen inside an ordinary star. Because ordinary stars do not have anything close to this density of free neutrons available. Something that is going to take these nuclei, these ordinary chunks of matter left over from the neutron star crust, and build them in seconds into the heaviest elements the universe contains. The mechanism is called rapid neutron capture, and it is one of the most beautiful and strange processes in all of physics. It happens in a burst, in the debris of two dead stars, in an environment so extreme that the nuclei are quite literally overwhelmed by neutrons faster than they can react through normal radioactive decay. That is the next piece of the story. How you take some ordinary iron nuclei, drown them in free neutrons, and end up with gold. The first thing to say about how gold gets made in a kilonova is that it does not get made by fusion. Not in the way stars normally make elements. Everything you have ever learned about how stars build the periodic table starts with fusion. Hydrogen fuses into helium in the core of a star. In more massive stars, helium fuses into carbon and oxygen. In the very heaviest stars, right at the end of their lives, elements as heavy as silicon fuse into iron in the final desperate seconds before the core collapses. That is the story most people know. Stars are element factories, and fusion is how they build the periodic table. But that story stops at iron. There is a very specific reason for that, and it is worth taking a moment to explain it, because it is at the heart of why kilonovae exist in the first place. When you fuse two light elements together like hydrogen into helium, the resulting nucleus is very slightly lighter than the two nuclei you started with. That tiny bit of missing mass got converted into energy, following Einstein's famous equation. Fusion releases energy. That is what powers stars. That is why the sun shines. This works all the way up until you reach iron. Iron sits at a special place in the periodic table. It is at the bottom of what physicists call the binding energy curve. What that means, in plain language, is that iron nuclei are the most tightly bound nuclei in the universe. Every neutron and proton in an iron nucleus is sitting at the lowest possible energy state that atomic matter can achieve. You cannot squeeze more energy out of iron by fusing it into something heavier. In fact, the opposite is true. Fusing iron into something heavier costs energy. It does not release it. That is why fusion in stars stops at iron. It is not that you literally cannot combine nuclei heavier than iron. You physically can if you supply enough energy. It is just that the process no longer pays for itself. In a stellar core where fusion has to release energy to keep the star from collapsing, iron is the end of the road. Once a star starts building iron in its core, its fate is sealed. There is no more fuel. Gravity wins. The core collapses. The star dies. So how does the universe make everything heavier than iron? Because we know it does. There is gold in your wedding ring. There is platinum in the catalytic converter of your car. There is uranium powering nuclear reactors. There is neodymium in the magnets inside your headphones. All of these elements are heavier than iron. None of them can have been made by ordinary stellar fusion. And yet, they exist. Something else is going on. The answer, worked out over decades of nuclear physics starting in the 1950s, is that you can build elements heavier than iron in a completely different way. Not by fusing nuclei together, by having existing nuclei absorb neutrons. This works because neutrons have no electric charge. When you try to fuse two nuclei, you have to overcome the electrical repulsion between them. Both nuclei have positive charge from their protons, and positive charges push each other away. Overcoming that repulsion is why fusion requires such extreme temperatures. You have to slam the nuclei together with enough energy that they get close enough for the strong nuclear force to grab hold of them, despite the electrical repulsion pushing them apart. But a neutron has no charge. It does not care about electrical repulsion. It can drift up to a nucleus and just be absorbed. No temperature requirement, no energy barrier. If a nucleus finds itself sitting near a free neutron, it will simply swallow the neutron, becoming a slightly heavier version of itself. That is neutron capture, and it is how the universe builds elements past iron. There are actually two flavors of neutron capture that happen in different environments. Astronomers call them the slow process and the rapid process, or the S process and the our process. The difference between them is not what they do. Both processes make heavy elements by adding neutrons to existing nuclei. The difference is the timescale. The slow process happens in certain kinds of aging stars, particularly in a phase called the asymptotic giant branch, where nuclear reactions in the star produce a modest flux of free neutrons. In these environments, a nucleus captures a neutron every once in a while, maybe once every 10,000 years, maybe once every million years. Between captures, the nucleus has plenty of time to do whatever else it wants. If the newly enlarged nucleus is unstable, it can undergo ordinary radioactive decay, transforming a neutron into a proton and moving to the next element up the periodic table. Then it sits there, stable, waiting for the next neutron to come along. Over millions of years, this slow process climbs up the periodic table, one element at a time, building things like strontium and barium and lead in ordinary stars. But the slow process has a limit. There are certain nuclei that are so unstable, so short-lived, that they cannot survive long enough between neutron captures to keep the chain going. When the slow process reaches one of these unstable nuclei, it stops. The nucleus decays, or fissions, or falls apart, and the chain breaks. That is why the slow process can only build so much of the periodic table. It cannot make the very heaviest elements. It cannot make gold, at least not in the enormous quantities that exist in the universe. It cannot make platinum. It cannot make uranium. The rapid process is what fills in the rest. The word rapid is doing a lot of work in that name, and it is worth being precise about it. Rapid here does not just mean fast. It means that neutrons are being absorbed by nuclei so quickly that the nuclei cannot undergo their normal radioactive decays between captures. Instead of capturing one neutron and then waiting to decay, a nucleus captures a neutron, and then before it has a chance to decay, it captures another neutron, and another, and another. The nucleus gets stuffed with neutrons faster than it can respond. This is exactly what happens in the ejecta of a neutron-star merger. In the seconds and fractions of a second after the collision, the density of free neutrons in the expanding debris is so extreme that any atomic nucleus sitting in that soup gets absolutely bombarded by neutrons. A single iron nucleus drifting in the ejecta can absorb dozens of neutrons in less than a second. Some might absorb over 100 before the neutron bath finally thins out enough for the process to stop. Think about what that means. You start with an ordinary iron nucleus, which has 26 protons and around 30 neutrons. That is iron 56, the most common form. Over the course of maybe a second or two, that same nucleus, still with its 26 protons, might end up with 100 neutrons, 120, in extreme cases, 150 or more. The nucleus becomes an absurdly overweight version of itself, not a different element yet. Still iron, technically, since the number of protons has not changed, but an isotope of iron with far more neutrons than any stable form of iron. These extremely neutron-rich nuclei are wildly unstable. Under normal conditions, they would fall apart in fractions of a second. In fact, most of them have never been seen in any laboratory on Earth. We know they exist only because our nuclear models predict they should exist, and because we can see the fingerprints of their eventual decay products in the light of Kilonova. But in the moment they are being built, in the ejecta of a neutron star merger, they persist just long enough for the neutron bath to keep stuffing them with more neutrons. At a certain point, though, the neutron bath thins out. The ejector has expanded so much that the density of free neutrons drops. Neutron captures slow down, and now, finally, the wildly overweight nuclei have time to do what they have been waiting to do. They decay. The decay chain that follows is where the magic really happens. An extremely neutron-rich nucleus has too many neutrons for its number of protons. It can restore balance by converting some of those neutrons into protons. The way it does this is called beta decay. A neutron inside the nucleus spontaneously transforms into a proton, emitting an electron and an antineutrino in the process. The total number of nucleons stays the same, but now there is one more proton and one less neutron, which means the nucleus has moved one step up the periodic table. An iron nucleus with 150 neutrons might beta decay once and become a cobalt nucleus with 149 neutrons, then decay again to nickel, then to copper, then to zinc, then to gallium, and on up the periodic table, one element at a time, as each excess neutron gets converted into a proton. The chain does not stop until the nucleus reaches a stable configuration, meaning a version of itself where the balance of neutrons and protons is stable enough to persist. For many of these chains, that means climbing dozens of elements. An iron nucleus that got stuffed with 100 neutrons might better decay its way through a chain of 40 or 50 different isotopes before finally landing on something stable. And along the way, the entire journey happens in seconds to minutes. That is how you build gold. There is one more layer of the rapid neutron capture process worth understanding, because it explains something you can actually see in the abundances of heavy elements throughout the universe. Not every step up the periodic table is equally easy. Certain nuclei act as bottlenecks. The process pauses briefly at these bottlenecks, and then resumes when the next neutron is captured. Nuclear physicists call these bottleneck nuclei waiting points. The reason waiting points exist has to do with the internal structure of atomic nuclei. Just as electrons in an atom organize themselves into shells, with certain numbers of electrons producing especially stable configurations, protons and neutrons inside a nucleus also organize themselves into shells. Certain specific numbers of neutrons, called magic numbers, produce especially tightly bound nuclei: 50, 82, 126. When the rapid neutron capture process reaches a nucleus with a magic number of neutrons, that nucleus is unusually stable. It resists absorbing the next neutron. It pauses. Meanwhile, other nuclei in the ejector keep climbing, so the process piles up material at the magic numbers before eventually breaking through. This piling up leaves a signature in the final abundance pattern. When astronomers measure the amounts of each heavy element in old stars, and in the sun, and in meteorites, they find distinct peaks at atomic masses of around 80, 130, and 195. Those peaks correspond directly to the magic numbers. They are the fingerprints of waiting points, preserved in the elements themselves. Gold sits near one of those peaks, which is part of why gold ends up being made in the quantities it does. There is one more feature of the abundance pattern worth mentioning, because it shows how carefully the fingerprints of the R process have been preserved. When astronomers measure the ratios of specific isotopes in very old halo stars, the pattern of the heaviest elements looks strikingly similar from star to star. Europium, gadolinium, dysprosium, and their neighbors all appear in almost exactly the same relative proportions in different ancient stars, even ones that formed billions of years apart and in different regions of the galaxy. That similarity is called the universal R process pattern, and it is one of the strongest clues we have that whatever process makes the heaviest elements does so in a reproducible way. The physics of the neutron bath, the waiting points, the magic numbers, and the decay chains all combine to produce roughly the same relative amounts of the heaviest elements, regardless of where or when the event happened. The absolute amount varies from event to event. The ratios, at least in the heaviest range, are remarkably consistent. A gold nucleus has 79 protons. To get from iron to gold, you need to move a nucleus up by 53 positions on the periodic table. That is a lot of beta decays, but it is exactly what happens in the aftermath of a neutron star merger, over and over, to enormous numbers of nuclei simultaneously, in an expanding cloud of debris the size of the solar system, all of them climbing the periodic table together at their own paces, ending up as gold, or platinum, or one of the rare earth elements, or uranium, depending on how many neutrons they absorbed and how their particular decay chain played out. The gold that ends up in your ring did not come out of a neutron star merger as gold. Not immediately. It came out as some incredibly unstable, overweight isotope of a much lower element, which then beta decayed its way up to gold over the course of many separate steps. By the time the ejector has cooled enough for stable atoms to form, the gold is there. But it was not there at the moment of the collision. It was assembled during the expansion in the debris cloud through a cascade of nuclear reactions that had never been possible anywhere else in the universe until two dead stars slammed together and made it possible. Now, there is a beautiful side effect of all this beta decay. It produces heat. Every time a neutron beta decays into a proton, it releases energy. That energy goes into the electron that gets emitted, and into the antineutrino, and into the recoiling nucleus. Some of it escapes the ejector cloud entirely as neutrinos, which fly away and are never seen again. Some of it escapes as electrons that get slowed down by the surrounding material. And a lot of it just heats up the ejector itself. You have enormous numbers of nuclei, all beta decaying at once. Each individual decay releases only a modest amount of energy. But when you multiply by the sheer number of nuclei involved, the total energy is staggering. The expanding ejector cloud is being heated from within by all this radioactive decay, and that heat is what powers the light of the kilonova. This is the crucial point I want you to hold onto. The light of a kilonova does not come from the neutron stars themselves. It does not come from the collision. It comes from the decay of the freshly built radioactive nuclei in the ejector, releasing energy as they beta decay their way toward stability. The kilonova glow is, quite literally, the light of gold and platinum and uranium being assembled in real time and radiating away the excess energy of their own creation. That is why kilonovae fade so quickly. Most of the beta decays happen within the first day or two after the merger. After that, the radioactive fuel starts to run out. The nuclei that are left have moved much closer to stability, and stable nuclei do not decay. Without a source of ongoing energy, the ejector stops being heated, and the glow fades. Kilonovae rise and fall over the course of days to weeks, not months or years like a supernova. They are brief, bright but brief. And after they fade, the atoms they made drift outward into the surrounding galaxy, eventually to be incorporated into new stars and planets, billions of years later. There is one more remarkable process worth mentioning here, because it plays a real role in what happens: fission recycling. Some of the nuclei that get stuffed with neutrons climb so high up the periodic table that they become too heavy to stay together. Elements past uranium are all unstable. Some are extraordinarily short-lived. When a very heavy nucleus fissions, it does not just decay, it literally splits apart into two roughly medium-sized nuclei, plus a scattering of free neutrons. Those free neutrons then go back into the neutron bath, where they can be captured by other nuclei that are still in the middle of climbing the periodic table. And the two medium-sized fission fragments themselves start climbing again from scratch, absorbing neutrons of their own. So the rapid neutron capture process is not just a one-way climb up the periodic table. In the most extreme cases, in the most neutron-rich ejector, it is a cycle. Nuclei climb to the top, split apart, and the pieces climb again. This fission recycling can happen multiple times for a single strand of material, which is one reason the process can produce such enormous quantities of very heavy elements. Every fission event resets some of the material to a lower atomic number and lets the process rebuild. Fission recycling is one of the more speculative parts of this whole story, in the sense that we cannot directly observe individual nuclei fissioning inside a kilonova. But the presence of the products of fission recycling in the abundance patterns we see in old stars gives us reason to believe it happens. The exact details are still an active area of research, and they matter for exactly how much gold versus uranium versus rare earth elements comes out of any given merger, okay? So we have neutron-rich ejector, we have rapid neutron capture, we have beta decay chains climbing the periodic table. We have radioactive heating. Now the last question. Why is the light of a kilonova blue for the first day or so, and then red and infrared for many days after? Why does the color change? The answer is a story about a specific family of elements, and about a very strange thing they do with light. You have probably heard of the lanthanides. They are the row of elements that sits at the bottom of most versions of the periodic table, tucked away in its own separate strip. Elements like neodymium and europium and gadolinium and terbium. 15 of them in total. They are called rare earth elements, though they are not actually all that rare on Earth. They are just chemically similar to each other and hard to separate, which is why they were called rare historically. The lanthanides have a very unusual electron structure. Their outermost electrons occupy a set of orbitals called the s orbitals, which are shaped in ways that make them extraordinarily good at absorbing light across a huge range of wavelengths. Any particular lanthanide element can absorb light at hundreds or even thousands of different specific wavelengths, corresponding to the enormous number of transitions its electrons can make. When you have a cloud of gas containing lanthanides, that cloud is remarkably opaque, especially at short wavelengths. Ultraviolet light gets absorbed almost immediately. Blue light gets absorbed too. Green and yellow light have a harder time getting through. Red light can penetrate somewhat further. Infrared light can penetrate deeper still. So a cloud that contains lots of lanthanides will preferentially let out the redder wavelengths, while absorbing and reprocessing the bluer ones. This is what determines the color of a kilonova. Remember what we said earlier. The ejector from a neutron star merger is not uniform. The equatorial region, dominated by tidal ejector, is the most neutron-rich part. It has the highest fraction of lanthanides and heavy actinides, because the highest neutron abundance allowed the rapid neutron capture process to climb to the heaviest elements. This equatorial region is loaded with lanthanides. It is extremely opaque at short wavelengths. The polar region, dominated by shock-heated ejecta and by some of the disk winds, is somewhat less neutron-rich. Neutrino irradiation may have shifted some of the neutrons into protons, which limits how high up the periodic table the rapid neutron capture process could climb. This region ends up with far fewer lanthanides. It contains lighter heavy elements like strontium and yttrium. Because it has fewer lanthanides, it is much less opaque at short wavelengths. Blue light can escape from it relatively easily. That is the physical origin of the two-component nature of the kilonova. In the first day or so after the merger, the kilonova is bright in blue and near ultraviolet wavelengths. This is because the polar ejecta, being lanthanide poor, is transparent enough to let blue light out. The polar material is also somewhat less dense than the equatorial material, so it becomes optically thin earlier. You get an early burst of relatively short wavelength light coming primarily from the polar regions of the ejecta. Over the next several days, the blue component fades, not because the ejecta stops radiating, but because the polar component was smaller and burned through its supply of radioactive fuel more quickly, and also because the whole thing has been expanding, cooling, and becoming diffuse. Meanwhile, the equatorial component starts to become visible. The lanthanide-rich material is dense and opaque, so it took longer to become transparent enough for its light to escape. When it finally does, that light is dominated by red and infrared wavelengths, because the lanthanides have absorbed almost everything shorter. For several weeks after a merger, the kilonova continues to glow in the near-infrared, powered by ongoing beta decays in the lanthanide-rich equatorial ejecta. Eventually even this fades as the radioactive fuel runs out and the ejecta expands into transparency at all wavelengths. That is why astronomers talk about a blue kilonova component and a red kilonova component. It is not that there are two separate explosions. It is one event, one expanding cloud of debris, but the cloud has different chemical compositions in different regions, and those different compositions produce different colors of light at different times. From the outside, it looks like the object changes color from blue to red over the course of days. But really what is happening is that we are seeing different parts of the ejecta at different times, dominated by different elements, radiating at different wavelengths. The shape of the kilonova light curve, the way the brightness rises and falls over time in each wavelength band, tells us a huge amount about what is in the ejecta. If the blue component is very bright, that tells us the polar ejecta has a lot of mass and relatively few lanthanides. If the red component is very bright and long-lived, that tells us the equatorial ejecta is massive and lanthanide-rich. If the light curve fades quickly, that tells us the total ejecta mass was small. If it fades slowly, the ejecta was more substantial. None of these light curves is exactly identical between different mergers. The masses of the two neutron stars, their spins, the geometry of the collision, the nature of the remnant, the amount of neutrino irradiation, all of these vary from event to event. Every kilonova carries the individual fingerprint of the particular merger that made it. Astronomers who study these events have to reason carefully about all of these factors when they try to interpret what they see. There is real uncertainty here. The nuclear physics that governs the rapid neutron capture process depends on the properties of nuclei that we have never studied in a laboratory. Some of these nuclei have hundreds of neutrons packed alongside relatively few protons, and their behavior has to be calculated from theoretical models rather than measured directly. Different models predict different rates for various nuclear reactions and different half-lives for various isotopes. When you feed different models into simulations of a kilonova, you get somewhat different predictions for what the ejector should look like. The abundances of gold and platinum and rare earth elements that get produced in any given merger depend on all of this uncertain nuclear physics. So when we say a single neutron star merger might produce something like an Earth's mass of gold, that number comes with real uncertainty. It could be more, it could be less. The exact quantity depends on the specific merger, on the composition of the ejector, and on the nuclear physics of the beta decay chains involved. What we can say with real confidence is that neutron star mergers produce heavy elements in enormous quantities, that those elements include gold and platinum and rare earths and uranium, and that the light we see from a kilonova is powered by the radioactive decay of the freshly built material. The details vary. The basic picture is solid. Once the ejector finishes fading, its atoms drift outward into the surrounding galaxy. Over millions of years, they mix with the interstellar gas. New stars form from that enriched gas, and around those new stars, planets form. Some fraction of the atoms that were built in a neutron star merger billions of years ago end up in the crust of a new planet. In some cases, they end up in the crust of a planet where, billions of years later, life evolves and eventually pulls those atoms out of the ground. That is not a metaphor. It is chemistry and it is history. The gold in the ring on someone's finger contains atoms that were assembled somewhere out in space in the debris of two neutron stars colliding, long before the sun and Earth even existed. Not every atom. We will get to the honest limits of that claim shortly, but some of them. Almost certainly some. Which brings us to the question of how anyone actually knows all this. Because the rapid neutron capture process is not something you can observe directly. You cannot see a single beta decay. You cannot watch a neutron get absorbed by a nucleus. What you can do is watch the light of a kilonova, measure how it changes, and reason backward from the physics to figure out what must have been happening in the ejector. And once, in a way no one had ever managed before, we got to do that while also detecting the gravitational waves from the very same merger. 3 completely different messengers, all pointing at the same point in the sky, all telling the same story. That is what happened in 2017. That is the story we are about to tell. For decades, everything we thought we knew about kilonovae was theoretical. We had the nuclear physics. We had the models of how 2 neutron stars would spiral together. We had detailed predictions for what the ejector should look like and what elements it should produce, but we had never actually seen one. Not properly. Not with the kind of certainty that turns theory into confirmed reality. That changed on the morning of August 17th, 2017. And when it changed in the most spectacular way possible. Not just one telescope catching a glimpse of something. Not just a single detection of light. It was 3 completely different kinds of signal, arriving from the same point in the sky within hours of each other, all telling the same story about the same event. Gravitational waves, a gamma ray flash, and then, over the following hours and days, a slowly evolving glow that changed color from blue to red as the world watched. That event is called GW 1708-17. The name comes from the date and the fact that it was detected in gravitational waves, and it stands as one of the most important observations in the entire history of astronomy. To understand why, you have to understand what it means to detect the same event through 3 different kinds of signal. Because each signal carries different information, and together they let us see the event in a way no single messenger could. Gravitational waves are ripples in space-time itself. As we said earlier, when 2 neutron stars spiral together, they emit gravitational waves that carry away the energy of the orbit. Those waves travel outward from the merger at the speed of light. When they reach Earth, they very slightly stretch and compress everything in their path. Not just the atmosphere, not just the buildings, the actual fabric of space through which everything moves. The stretching and compressing is unimaginably tiny. When a gravitational wave from a neutron star merger 130 million light-years away passes through Earth, it changes the distance between 2 objects on the ground by something like 1 part in 10 to the 21st. That is a length change about 1,000 the diameter of a proton, over a distance of several kilometers. Detecting a change that small requires instruments so sensitive that they are essentially at the limit of what physics allows. Those instruments exist. In the United States, there are 2 facilities called LIGO. LIGO stands for the Laser Interferometer Gravitational Wave Observatory. There is one in Louisiana and one in Washington State, on opposite sides of the continent. Each one consists of 2 4-kilometer-long tunnels arranged in an L shape, with the laser beams bouncing between mirrors at the ends. When a gravitational wave passes through, it stretches one arm of the L by a tiny amount and compresses the other. That stretching shifts the interference pattern of the laser light, and the shift is what gets detected. In Italy, there is a similar detector called Virgo, with 3-kilometer arms. Together, these 3 detectors form a network. When all 3 see the same signal at slightly different times, based on how long the wave took to travel from one to the next, you can triangulate roughly where in the sky the signal came from. That was crucial for what happened next. On the morning of August 17th, 2017, at 12:41 Coordinated Universal Time, all 3 detectors picked up a gravitational wave signal. It was a chirp. Exactly the kind of chirp predicted for 2 neutron stars spiraling together. The signal started at a low frequency, tens of hertz, and climbed upward over the course of about 100 seconds. That is a long signal by gravitational wave standards. Black hole mergers give shorter, more powerful chirps. This one lasted longer because neutron stars are much less massive than the black holes previously detected. It took them longer to sweep through the frequency range the detectors could see. The signal peaked, and then it cut off. That was the moment of merger. Within 1.7 seconds after the gravitational wave signal ended, a gamma-ray flash arrived at Earth. It was detected by 2 space-based gamma-ray observatories, NASA's Fermi satellite and the European Space Agency's Integral. Both instruments picked it up. It was a short gamma-ray burst, lasting less than 2 seconds, exactly the kind of burst that theorists had long predicted should accompany neutron star mergers. Think about that timing for a moment. The 2 signals arrived within seconds of each other, and they came from the same direction. This was not a coincidence. This was a direct observational demonstration that short gamma-ray bursts are made by neutron star mergers. For decades, that had been the leading theory, but no one had ever proven it. In 2 seconds, on the morning of August 17th, the case was closed. Neutron star mergers produce short gamma ray bursts. We now know this because we watch one do it, but that was only the beginning. The gravitational wave signal, combined with the timing information from the gamma ray burst, gave astronomers a rough patch of sky where the event had occurred. Rough is a relative term here. The uncertainty region covered about 30 square degrees, which is a large area of sky. For comparison, the full moon covers about half a degree, so the search area was roughly 60 times the width of the moon. But astronomers had never been asked to search a patch of sky like this before. They had never been chasing an electromagnetic counterpart to a gravitational wave signal. It was a completely new kind of astronomy. And so, within hours of the gravitational wave alert going out, telescopes all over the world started slewing to the search area, trying to be the first to spot whatever visible light was coming from the merger. The event happened in the southern sky, so telescopes in the southern hemisphere had the best view. A team using the SWOPE telescope at Las Campanas Observatory in Chile spotted something new that had not been there in previous images of the same field. A bright new point of light near a galaxy called NGC 4993, roughly 130 million light years away. They called the new object SSS 17A. It was the optical counterpart. It was the Kilonova. The story of how that discovery actually happened deserves a moment, because it is one of the great sprints in the history of astronomy. When the gravitational wave alert went out from LIGO and Virgo, it triggered a scramble unlike anything astronomy had seen before. Dozens of teams around the world had signed up in advance to search for optical counterparts to gravitational wave events. Now, the alert was real. The clock was ticking. The kilonova, whatever it looked like, would fade within days. Nobody knew exactly what to look for, but everyone knew that whoever found it first would help write the history of the field. The search area, 30 square degrees of southern sky, contained tens of galaxies within the plausible distance range implied by the gravitational wave signal. Different teams pursued different strategies. Some slewed across the entire uncertainty region, taking rapid images. Some prioritized specific galaxies based on their masses and star formation histories. The SWOPE telescope team took the second approach. They had prepared a list of nearby galaxies within the localization region. They started working through the list systematically. Almost 11 hours after the gravitational wave detection at the 9th galaxy on the list, they saw it. A new point of light next to a galaxy called NGC 4993 that had not been there in previous images. Within about an hour, several other teams independently spotted the same object. The confirmation was fast, because the object was there, glowing in real time, exactly where the gravitational wave detectors had said something ought to be. Almost immediately, telescopes around the world converged on the same object. Within hours, dozens of teams had it in their sights. The Hubble Space Telescope was tasked to observe it. Ground-based telescopes across multiple continents took spectra of it. Radio telescopes tuned in. X-ray observatories pointed at it. Every wavelength of the electromagnetic spectrum that we can observe was brought to bear on this one object in the days after the merger. And what they saw was, in every important respect, what theorists had been predicting for years. Early on, the object was blue, bright at short wavelengths, including in ultraviolet where the SWIFT satellite was watching. Over the next day or so, the blue faded rapidly. By day 2 or 3, the object had turned distinctly redder. By day 5, it was clearly dominated by red and near-infrared light. By day 10, it was mostly infrared and fading. Over the next couple of weeks, it faded away entirely at optical wavelengths, though the infrared glow lingered longer. This color evolution was exactly what the theory predicted. A blue component, dominated by lanthanide poor polar ejecta, brightening and fading quickly. A red component, dominated by lanthanide-rich equatorial ejecta, taking longer to become visible and lasting longer as it faded. Two components in one expanding cloud, seen from the outside as a color-changing glow. The spectra told an even richer story. When astronomers used spectrographs to break up the light of the object into its component wavelengths, they saw absorption and emission features that could be matched to the presence of specific elements. Early on, the spectra showed features that appeared to be consistent with lighter, heavy elements like strontium. Later, the spectra were consistent with the presence of large amounts of lanthanide-rich material. Though identifying individual lanthanide elements in kilonova spectra is genuinely difficult because so many elements produce overlapping features and the ejecta is expanding at speeds that broaden every spectral line into a blur. Still, the overall shape of the light curve, the color evolution, and the general character of the spectra all pointed to the same conclusion. The rapid neutron capture process had been operating in that ejecta. Heavy elements had been assembled. Radioactive decay was powering the glow. Kilonova theory, worked out over decades, was being confirmed in real time by a live event we could actually watch. Estimates of the amount of heavy element material produced in this one merger vary somewhat, depending on which model you use to fit the light curve. But most estimates land in the range of a few hundredths of a solar mass of total heavy element ejecta, with something on the order of an Earth's mass worth of gold, more or less, being one plausible piece of that total. The uncertainty on that gold estimate is large. Different models give different answers, sometimes different by a factor of several. But the general picture is that a single merger like this one produces heavy elements in quantities that are staggering by any earthly standard. One event, one collision, one kilonova. Enough gold to reshape a planet, all of it built in the seconds and minutes following the collision, assembled from iron nuclei and free neutrons by the beta decay chains we described earlier. And crucially, we watched it happen in three completely independent kinds of signal. Gravitational waves told us that two very compact objects had spiraled together. The gamma-ray flash told us that a relativistic jet had been launched. And the optical and infrared glow told us that a substantial amount of neutron-rich material had been ejected and had built heavy elements through the rapid neutron capture process. That combination gave us more than any single messenger could. It was the birth of what astronomers now call multi-messenger astronomy. Not one channel of information about a distant event, but three, arriving from the same point in the sky, cross-checking each other in real time. Before we go any further, I want to be honest about some of the caveats around GW170817, because they matter. The gamma-ray burst we saw from this merger was actually rather weak by short gamma-ray burst standards. It was much less bright than most short bursts we had seen from more distant sources over the years. That tells us something important about the geometry. The jet from the merger was probably not pointing directly at Earth. If it had been, we would have seen a much brighter gamma-ray flash. Instead, the jet was probably angled somewhat away from us, and we saw only its edges, or possibly the emission from surrounding material that got shocked by the jet as it broke out. That geometry is why the burst was weak. This is a critical point for understanding kilonovae in general. You do not need the jet to be pointing at Earth to see the kilonova itself. The kilonova glow radiates in every direction because the ejector is spread out around the merger site in a broad cloud rather than being concentrated in a narrow beam. Even if the gamma ray jet completely misses us, we can still see the kilonova, provided the merger is close enough. Most kilonovae we detect in the future will probably be like this: bright optical and infrared counterparts without necessarily a coincident bright gamma ray burst. Another important caveat is that GW 170817 was, by neutron star merger standards, remarkably close. 130 million light years is not close by any human measure, but most detectable neutron star merger events happen much farther away. This one was close enough to be relatively bright, close enough for detailed spectra to be taken with existing telescopes. Most future events will be dimmer, harder to characterize, and will require more powerful instruments to study in detail. And GW 170817 was one event. 1. That is not enough to declare that all kilonovae behave exactly like it. Every merger will have somewhat different masses, spins, and geometry. The one we saw is a data point, not a template. The confidence we have in kilonova theory comes from the combination of theoretical prediction plus this one confirmation, plus the fact that pieces of the story hold together across many independent lines of evidence. Since 2017, LIGO and Virgo have detected a small number of additional neutron star merger candidates. Most of them have not had confirmed electromagnetic counterparts. That is partly because they were farther away, and partly because, for some of them, the sky localization was too imprecise to allow telescopes to find the optical counterpart before it faded. Finding kilonovae remains difficult. The glow fades quickly. You have to search a larger area of sky, in the right wavelengths, on the right timescale. It is not easy. Future gravitational wave detectors will help. Facilities under construction and under proposal, including upgrades to existing detectors and entirely new instruments, will be able to detect neutron star mergers farther out, with better sky localization, and will give telescopes a better chance of catching the light. Wide field survey telescopes coming online in the next several years will be able to search large patches of sky quickly, catching kilonovae in their first days. Infrared observations will be particularly important because so much of the kilonova light emerges at long wavelengths, especially from the lanthanide-rich equatorial ejector. The James Webb Space Telescope has already been used to look at kilonova candidates. Future infrared observatories will help characterize the mid-stages and late stages of these events better. And with more events, we will be able to look at kilonovae from different viewing angles. Some events we will happen to see edge on, some from the pole, some from angles in between. Each perspective will teach us something about the geometry of the ejector and about how the properties change with viewing angle. Over the next decade or two, if we are lucky, we will have observed enough kilonovae to start building real statistical understanding of the population, not just extrapolating from one landmark event. Now, let me turn to what is probably the most important honest caveat of the entire story. And it is one that popular accounts of this topic often skip over, so I want to spend some real time on it. The question is this: are neutron star mergers the source of all the gold and heavy elements in the universe? The short answer is that we do not know for sure, and the current best guess is probably not all of it, probably a significant fraction, maybe most of it for some elements, but almost certainly not the only source. Here is the situation. When astronomers survey the abundance patterns of heavy elements in various environments, in the sun, in old stars, in the halo of our galaxy, in dwarf galaxies, in gas clouds at high redshift, they find that heavy elements are pretty widely distributed. Even very old stars, formed early in the history of the universe, sometimes contain heavy elements in their spectra. That is a puzzle, because to enrich those old stars, you need heavy elements to have been produced and dispersed early enough in cosmic history. Neutron star mergers are rare and, on average, they happen relatively late in the life of a galaxy. It takes time for two massive stars to be born, for both of them to explode as supernovae, for the resulting neutron stars to spiral together over hundreds of millions or even billions of years, and finally to merge and eject heavy elements. That is a long time scale. For very old stars in the halo of the galaxy which formed early, there might not have been enough time for neutron star mergers to have significantly enriched the gas from which they formed. This tension has driven a lot of research into whether there might be other sources of heavy elements that operate earlier and faster. The leading candidate for that other source is called a collapsar. A collapsar is a very massive, rapidly rotating star that, when it dies, does not just make a black hole quietly. It makes a black hole surrounded by an accretion disk, and the accretion disk can support conditions similar to those in a neutron star merger. Extremely dense, extremely neutron-rich material that can undergo rapid neutron capture and produce heavy elements. Collapsars are also thought to power a certain kind of long gamma ray burst, which is a different phenomenon from the short gamma ray bursts associated with neutron star mergers. If collapsars produce heavy elements, they would do so on a much shorter timescale than neutron star mergers, because a very massive star lives only a few million years before dying. That would give collapsars time to enrich the gas that later forms old stars, in a way that neutron star mergers might struggle to do. The evidence is mixed. Some heavy element abundance patterns in old stars look more like what you would expect from collapsars. Others look more like what you would expect from neutron star mergers. The truth may be that both processes operate, contributing to different fractions of different elements. Neutron star mergers may dominate for the very heaviest elements, like the actinides and the heavier lanthanides. Collapsars may contribute more to the lighter heavy elements, or the split may be different from that. Nobody knows for certain yet. This is an active area of research. What we can say is that neutron star mergers definitely produce heavy elements, in enormous quantities, in real events we have observed. GW 170817 confirmed that. Kilonova theory is broadly correct. The rapid neutron capture process happens in the ejecta of these mergers. But the total contribution of mergers to the universe's heavy element budget, relative to other possible sources, remains uncertain. Some fraction of gold, some fraction of platinum, some fraction of uranium, but not necessarily all of it, and not necessarily even most of it, depending on which element you are asking about. That honest uncertainty does not diminish the discovery. If anything, it makes the story richer. The universe has multiple ways of building heavy elements. Some are exotic, some are still being figured out, but we know for certain now that at least one of the ways involves the debris of two dead stars colliding, and we have actually watched it happen. There is a broader payoff to studying kilonovae, beyond just the question of where the elements came from. Kilonovae also serve as unique laboratories for nuclear physics, under conditions no earthly experiment can reach. By studying the light of kilonovae and comparing it to detailed simulations that include different nuclear physics models, we can actually test our understanding of how atomic nuclei behave when they are extremely neutron-rich. Which nuclei are the bottlenecks in the process? What half-lives they have? Whether fission recycling is really happening. All of this can, in principle, be constrained by careful observation of kilonovae. Neutron star mergers also give us information about the equation of state of neutron-rich matter. In plain language, that means, how does matter behave when it is compressed to the densities inside a neutron star? What is the relationship between pressure and density under those conditions? This is a fundamental question in nuclear physics, and it is closely tied to the maximum mass of a neutron star, to how much a neutron star gets tidally deformed just before merger, and to whether a given merger produces a neutron star remnant that lasts for a while or immediately collapses into a black hole. Gravitational wave measurements from mergers can constrain some of this. The tidal deformation of neutron stars during the final moments of inspiral leaves a subtle imprint on the gravitational wave signal. From that imprint, we can start to say something about the properties of the neutron star matter. Combined with the electromagnetic observations, we can potentially say even more. Different equations of state predict different amounts of ejecta for a given merger, and the amount of ejecta shapes the kilonova we see. This is beautiful in a very deep way. A gold ring on someone's finger, and the fundamental physics of matter at the highest densities the universe allows, turn out to be closely connected. Both are shaped by the same underlying processes. The physics of neutron-rich material at extreme densities, and what happens to that material when it gets flung into space. Let me pull the whole story together now. Two very massive stars are born together in a binary system, somewhere out in the galaxy. Both of them live fast and die in supernova explosions, leaving behind two neutron stars. The two neutron stars, still bound by gravity, begin to orbit each other in the dark. Over hundreds of millions or billions of years, they emit gravitational waves that slowly bleed energy from their orbit. They spiral inward. The orbit shrinks. The orbital speed rises. The gravitational waves become more powerful. In the final second before collision, they are whipping around each other at nearly the speed of light. Then they touch. At the moment of collision, tidal forces have already torn ribbons of material away from each star. Shock-heated ejecta squirts out at the interface as the two stars ram into each other. The merged remnant, which may be a hypermassive neutron star that lives for a moment before collapsing into a black hole, or a longer-lived neutron star, or a prompt collapse into a black hole, is surrounded by an accretion disk of leftover material. That disk drives winds outward over the following seconds and minutes. Together, the tidal ejecta, the shock-heated ejecta, and the disk wind ejecta form a lopsided cloud of debris expanding outward at 10 to 30% of the speed of light. The equatorial region is drenched in free neutrons. The polar region is somewhat less neutron-rich. Inside this expanding cloud, ordinary nuclei absorb enormous numbers of neutrons in rapid succession. They become wildly overweight, unstable isotopes. Then, as the neutron bath thins out, they beta decay their way up the periodic table, one element at a time, into gold, platinum, rare earth elements, and uranium. Each decay releases energy. That energy heats the ejector. The heated ejector radiates, and that radiation, escaping the expanding cloud over the following days, is what we see as a kilonova. Meanwhile, if the geometry is right, a jet from the central remnant launches at nearly the speed of light and produces a brief gamma ray burst. If the jet happens to be pointing roughly at Earth, we see it. And through all of this, the gravitational waves from the inspiral and merger are propagating outward at the speed of light, ready to be picked up by instruments sensitive enough to detect distortions in space-time. The freshly built heavy elements, once the kilonova fades, drift outward into the surrounding galaxy. Over millions of years, they mix with the interstellar medium. New stars form from this enriched gas. Around those new stars, planets form. Some of the atoms end up in the crust of a rocky planet. Some end up in ore veins. And billions of years later, on a planet whose crust contains atoms forged in a violent collision long before the planet even existed, a civilization mines those atoms out of the ground and makes rings and coins and industrial catalysts from them. Not every gold atom on Earth came from a kilonova. Some almost certainly did. Others may have come from collapses, or from processes we are still figuring out. But at least some of the gold on Earth was built in the debris of two neutron stars colliding, somewhere out in the young Milky Way before the sun was born. That is the story a kilonova tells. Two dead stellar cores meeting in the dark. A collision that lasts less than 1,000th of a second. Ejector thrown outward at nearly the speed of light. A cascade of nuclear reactions that couldn't happen anywhere else in the universe. A glow that changes color as it fades over days. And the enrichment of everything that comes after. New stars, new planets, new atoms in the crust of new worlds. The gold in the ring on someone's finger did not have to be made peacefully inside an ordinary star. Some of it, at least, was assembled in the neutron-rich wreckage of two corpses colliding, in a fireball that lit up its own creation as it happened. The universe is stranger than that. It is stranger than a peaceful furnace. It is stranger than a quiet star. It is a place where death, when it happens at the extreme, can also be creation. Where two dead things, coming together, can build atoms that no living star could ever assemble on its own. And every time you hold a piece of gold, you are holding something that was probably assembled in that impossible violence. Long before Earth, long before life, in the debris of a collision so extreme that it briefly outshone every ordinary star in a large galaxy combined, in gravitational waves, radiating light, radiating neutrinos, radiating the heaviest atoms the universe knows how to make. Sleep well tonight. The gold in your world came from a place stranger and more violent than most people ever imagine. And that is not sad. It is beautiful. It is the universe telling its own story in the ashes of the dead, written into the atoms of the living.